The domain of this function is every x value from here over. Yes. So the lowest value is -5, and it goes all the way up to infinity. Do we include -5? Yes. -5 is part of the domain, and we can never include infinity because we can't get there. Okay. The range is every y value from here up. So the range is going to be from -4 to infinity. Do we include -4? Nope. Yes. Sorry. We include -4, but we do not include infinity. You gotta watch me. I don't really know what I'm doing. Okay. Positive values. The positive values are found along that interval and along this interval. So how would we describe that first set of positive values? -4 to 1. Do we include either of those endpoints? No. Why not? At -4 and at 1, the graph is on the x-axis, which is y equals 0. So that is not a positive number. How do you describe that second set of positive values? 5 to infinity, and we don't include either of those. Okay. Negative values are found here and here. How would you describe that first set of negative values? -5 to -4. Do we include -5? Yes, we do. Because it's part of the graph, or it's not 0. It's a negative value. Do we include -4? Nope, not included. And then the last one is from here to here. So from 1 to 4, and neither of those points are included. Oh, is it 5? Sorry. From 1 to 5. And neither of those points are included. Okay. Increasing and decreasing. The graph from there to there is increasing. And then from, the next interval, from there to there, the graph is decreasing, and then everything else is increasing. Everybody understand how I split that up? We just cut it into the ups and the downs. So for increasing, my first interval is from -5 to -1. Do I include either of those? I do include the -5. Not because it's not touching, because it's not the top of a hill or the bottom of a valley. Okay, the only time that we don't include a point for increasing and decreasing is if the graph is flat at that point. So, remember I drew my little car the other day? And if I drive this car up the hill, at that number we are going up, but it's at -1 we've reached the crest of a hill, and we're not increasing anymore. If I come down the hill and I bottom out, at -1 and at +2, I'm going perfectly horizontal, just for an instant. So we do not include -1 and we do not include 2. But we are going to include -5 because at -5 I'm going up. So the other increase begins at 2 and goes to infinity, and I don't include either of those endpoints. What is the interval of decrease from -1 to 2? Do I include either of those? Nope. Okay. Today we're going to talk about what is called end behavior. So if you open your books to page 36. It's okay. If you don't have it, you can look at mine. So on page 36, you see the definition of end behavior. And it says, end behavior describes what is happening to the y values of a graph when x goes to the far right, which is positive infinity, or x goes to the far left, which is negative infinity. So it's sort of like increasing and decreasing, except we don't have any actual values. We're wondering what happens when the graph goes towards infinity. So if we look at the first example, we see a line, and it says it wants to use this notation, the limit as the function, which is negative 4x plus 3. As x approaches infinity, then the graph approaches what? Well, this is a calculus notation, and it's really useful in calculus, but it's not terribly useful for what we're going to do, so we're not going to make you write all that down. We're just going to write it this way. As x approaches infinity, y approaches, and then we just need to figure out what the answer is. So you don't need to write the limit and the function and all of that. So if we look at this graph, if we travel to the right, if my x's go to the right, what direction is my y traveling? Down. So y is approaching negative infinity. Does everybody get that? So as x goes to the right, y is going down. The next part, as x approaches infinity, negative infinity, then y approaches. So if I look at the graph, if I travel left, where's the graph going? Up. And up would be infinity. So as we go to the right, the graph goes down. As we go to the left, the graph goes up. So look at the next example below there. So on this one, as x approaches infinity, y approaches. So as we travel to the right, you'll notice that the graph is going down. So negative infinity. Okay. As x approaches negative infinity, so as the graph travels to the left, as x travels to the left, where does the graph go? Down. So y approaches negative infinity. Okay? And if you're working ahead, you're doing it the hard way. There's a much easier way to do it than graphing it. So, just to warn you. So the next one, as x approaches infinity, and sometimes instead of saying y, they use f of x, which is the name of the function. So f of x and y are the same thing. G of x and y are the same thing. So in your answers for the assignment today, it's actually going to say f of x approaches whatever. So in this graph, as x gets bigger, what happens to the function? Going up or down? Up. And it's going up really slowly, but it's never going to level out in this case. So f of x approaches infinity. As x approaches negative infinity, what does f of x do? It doesn't exist. There are no y values left of x equals 2. So if I try to travel to the left, I can make it to there, and then I can't go any further. So there is no graph to the left, which means that the limit doesn't exist. Now this is not a case where you can do the empty set, because we're looking for a direction. We're not looking for a number. So you can't use this funny symbol. You just need to say that there is no limit, or it doesn't exist. Okay? Before we move on, I want to talk about graphing polynomials. What does an x squared graph look like? It's a U. What does an x to the third graph look like? So, from what I've seen, something like that. What does an x to the fourth look like? It can look like an x squared, but it could also look like that. How do I know? Okay, that exponent tells me how many possible answers there are, how many possible zeros there are, how many possible x-intercepts. So, if I drew a graph, that only has one x-intercept. That's an x to the first graph. That has two x-intercepts. It's an x squared graph. That would be an x to the third graph. So really, I can create as many wobbles as I want. So this would be an x to the first, second, third, fourth, fifth, sixth, seventh, eighth. Okay? The number of direction changes tells you what type of polynomial the function is. Okay, but having said that, an x to the 8th graph doesn't actually have to hit 8 times. This could be an x to the 8th. Okay, or this could be an x to the 8th. But there's one big thing we notice about even numbers and odd numbers. What's the difference between even numbers and odd numbers? The end behavior. On an even numbered polynomial, the end behavior is in the same direction. So what do I know about that polynomial? It's odd. Does it have to be an x to the 5th? No, it could be. What else could it be? It could be x to the 7th. Anything else? Any 23rd, 109th. What do we know it can't be? It can't be an x to the 2nd because we know it's odd. It cannot be an x to the 3rd because it crosses 5 times. So it's either an x to the 5th or a bigger odd number than 5. Okay? There's something else I know about it that we haven't talked about yet. What's the difference between this graph and that graph? So this one is an x squared, or what else could it be? Any even number bigger than 2. Okay? What is this graph? Negative x squared, or any other even number bigger than 2. Okay? What about what do we know about that graph? It's odd, so it's x to the, what's the smallest one it could be? 7. What do I know about the sign? Positive. Okay? So, if I had a positive x to an even number, then I know that the graph is going to look like this. I have no idea what happens in the meantime. Okay? it could come down and back up. It could come down and wobble a bunch of times and then go up. We don't know. But if it's even, I know if it's a positive x to an even number, it's up and up. If I have a negative x to an even, what would that look like? It would be down, and whatever happens in the middle happens. We're not sure. Okay? What about a positive x to an odd? Left side goes down, right side goes up, and whatever happens on the inside doesn't really matter. Everybody catching on to this? And then a negative x to an odd value. Left side's up, right side is down, and who knows what happens in the meantime. Okay? Well, the neat thing about polynomials, if I have 6x to the fourth minus 10x to the fifth plus 2x plus 1, I know what the end behavior is going to be without graphing it. It's the biggest exponent. So it's this term. That term determines the end behavior. What is the end behavior going to be? As x approaches infinity, so as the graph goes to the right, what's it going to look like? It's going to go down. How do we know it's down? Well, if I look back here, it's a negative odd. And the negative odd starts on the top and ends on the bottom. Okay? As x approaches negative infinity, y approaches infinity. So I know the graph looks something like this. I don't know what happens in the meantime. Yes, this is the answer. Now, what do these other numbers do to the graph? They determine how many of those wobbles actually appear. They determine how high and low the wobbles are and how wide they are. But this first term, the sign of the biggest term and the exponent of the biggest term, that determines the end behavior. All the other numbers just change the shape of the graph. And that biggest exponent determines whether it's going up or down as you travel to the left or to the right. Is that going to make things easier for you? Yeah. So if you forget, if I look at this and say, I don't remember what the rules are, don't graph the whole equation. Because you might graph the equation and get this. Because the graph is so big, you don't have any idea where it's headed. So if you're going to graph it, just graph the only term that's going to change the end behavior. Your graph won't look right, but the end behavior will be right. Okay? What if I had a graph like this? As x approaches negative infinity, so as the graph goes left, where is y headed? Well, as x goes to negative infinity, how high is the graph going to be? Is it going up or is it going down? It's going down, but it's not going to negative infinity. What y value is it approaching? It's approaching negative 3. So as I trace my x's, negative 1 on my x, I'm 10 on my y. Negative 3 on my x, I'm at 0. Negative 4, I'm at negative 1. Negative 5, I'm at negative 2. And the further I go this way, the bigger my x's get, or smaller, that y value gets closer and closer to 3. Okay, what about the other side? As x goes to the right, my y value is getting closer and closer to negative 3. Yes. This one would be negative x over, well, no. negative 2 over x, and this one's minus 3. Okay, what if I had this graph? As x approaches negative infinity, what happens to my f of x? Goes up. So the answer is infinity. But as x approaches infinity, what happens to my f of x? It's approaching the number 0. It's getting closer and closer to y equals 0. Now, you won't see any of those on your worksheet today. Everything on your worksheet is polynomials. And all polynomials either go up or down. They don't approach a number. Okay? So today you're going to finish that. Tomorrow we're going to do kind of a group review. The next day we are going to take the practice test, and the day following that will be the test. Okay? Get to work.